All right, hello class. In this video, we're going to be starting our Calculus 3 journey, and we're going to start with what for some of you will be review, and for others might be brand new. So if you have learned vectors before, you can feel free to go ahead and jump to when we start talking about vector valued functions, curves in space. But this is going to be basically the basics of vectors here. Okay, and so we're going to be talking about what vectors are and how to manipulate them, their basic operations, so on and so forth. Okay, so before we get onto that, though, I do want to take time in this particular lecture to introduce Calculus 3 and what it is we'll actually be doing, and then hopefully it'll make some sense as to why we start with vectors when we do that. All right, so Calculus 1 and 2, it's what you're familiar with, is what you might consider one-dimensional problems. And you might be thinking, hang on. That doesn't make sense. Everything we looked at was two-dimensional. And you're right. We had an independent variable. So we would always have one independent variable. And one dependent variable. Okay, so our independent variable, you could usually think of that as x or time, we and our dependent variable, that would be usually y, but it could be other things. We were usually looking at this as y equals some f of x, or y equals some f of t, and the derivative, our calculus, was always like a dy over dx equals f prime of x kind of stuff. Okay, so some would argue it's two-dimensional because as you chart one variable towards another, you do get a 2D graph when you do that. Right, this would be our y equals f of x, for example. But others would say it's one-dimensional because we're only looking at, say, a single independent variable. Okay, so what does Calculus 3 do? Well, Calculus 3 moves all of our calculus stuff to multiple dimensions. So here we're going to move to 2 and 3D, or multiple dimensions of any kind. It doesn't just have to be up to 3 dimension. We could do 4 dimensions where we have 3 spatial and 1 time. We could have an economics problem where we have like 10 dimensions, and each one of those is some sort of force acting on the economy. Okay. So there are multiple ways that we can go about this. So we could have 2 to 3 independent variables with 1 dependent variable. Okay, we could have, so that's the first, or not really the first, but that's one way we could do this. We could have 2 to 3 dependent variables and 1 independent variable. Okay, or we could combine the two and have 2 to 3 dependent variables and 2 to 3 independent variables. And so this is the main goal here, is to do calculus with multiple variables. But to do that, we first start, we really start here with more than one dependent variable and one independent variable, and then study the multiple independent variables and then combine them. Okay, so how we go about that, our first step into this with the one independent variable and multiple dependent variables, we go through this through vectors. Okay, so let's talk about what vectors are and just start rock and rolling from there. Okay, so the first question, of course, is what is a vector? A vector is a mathematical object that was created to represent forces. Okay, and it can really represent any force. It can represent actually gravity. It can represent electrical forces. It can represent movement. Newtons, you know, there's really any kind of force, and things outside of physics it can also represent. So it's basically a mathematical object created to represent forces, and it comes with two components. Okay, two components. A length, which I'll often call the magnitude, and direction. Well, I think direction is self-explanatory. It's the direction the force is being applied in, the direction that the person is running in, etc. And the length and the magnitude, well, the length corresponds to the magnitude of the force, and this is what makes vectors work. Okay, so the length itself directly corresponds to the amount of force. How I like to think about it is if you double the length of a vector, you're talking about double the amount of force. So vectors are basically arrows, right? That's how we represent them. We represent them as physical objects in space as arrows. So the length is the amount of force, right? It's the actual magnitude of the force. So if I draw an arrow that is in the same direction but twice as long, right? This is twice the force, twice the amount of force. Okay? And this is what really makes a vector work, vectors work. So whoever came up with this just thought, all right, let's just represent forces as arrows that point in the direction of the force, and then the length corresponds to the magnitude of the force, and turns out it works. It is mathematically sound, it's mathematically accurate, and it works out exactly how we would want it to. It actually, once we get down into the nitty-gritty of how we talk about these things mathematically, it just works. Okay, so let's start talking about how we represent or talk about these things mathematically. Okay, so when we first start talking about a new mathematical object, whether it's numbers or matrices or vectors or functions or what have you, we want to start talking about it in terms of operations. And the first one we want to talk about is equality, right? When are two vectors equal? Well, it turns out two vectors are equal if they have the same direction and the same magnitude. All right, now notice I did not say anything about position, right? So this vector here, let's say it makes a 45-degree angle, and it's this length, and I'm going to call this vector v. I'll talk about how we notate these in a second. And then I draw another vector here, same angle. Suppose I'm actually drawing this right. This is still the same vector, right? Position does not affect equality, right? So these are still equal even though they're in different positions. And hopefully that makes sense when it comes to forces, because if I'm standing over here, right, my weight is going to be affected by, let's say, gravity. And if I walk, I don't know, 5 feet over, my weight's likely going to be exactly the same, right? If I'm walking across a flat surface, if I'm not climbing up stairs or climbing up a mountain or something, it'd be nice if I could lose a few pounds just walking 5 feet, but probably not. But in general, yeah, my weight here and my weight 5 feet from here is going to be the same, right? It's the same force being applied on me. A force of 5 newtons, let's say this is a 5 Newton force here pointing in this direction, is the same force applied to maybe this box as it would be over here applied to this rock. It's the same force. So these vectors are the same. They're equal. Okay? They might be acting on different objects or act from different positions, but they are still the same vectors. So because of that, we have what's called a standard form of a vector. All right, so since position doesn't affect equality, we can define all of our vectors in a standard way. In that way, well, if I just draw any vector, okay, now usually the book will use bold letters for vectors. Since it's difficult to do that, the standard notation for when you're just writing it by hand is to put an arrow, but I don't like, it takes too long to do the full arrow for me, so I always do this little guy. But I know some physicists will use something like this, the little caret or dots or other things, right? There are a lot of notations we can use. I'm just sticking with this one to keep it consistent, okay? But the book will use bold. Okay, so each vector in 2D space, we're just talking about 2D vectors here. Okay, we'll talk about 3D vectors in just a second, but it all works the same way. It's just a little tougher to visualize. So since position doesn't affect equality, each vector we can define as the triangle it makes, right? Because it will go a distance in x, so I'll call this delta x, and it will go a distance in the vertical direction, which I'll say is delta y, right? It will have an amount it travels in the along the x-axis, and an amount it travels along the y-axis. And because every vector does that, right? Any vector I draw, I can make this triangle with it. We get in the habit of labeling vectors as, well, let's say this is my v. We write it like this. We use a sharp bracket, which kind of corresponds with vector, an arrow. We do that to make it easier to distinguish between points, and we'll get to that in a second. But anyway, it will be delta x in the first component, delta y in the second component, and we close it off with a sharp bracket. Now, sometimes you'll see books that will use just normal parentheses. You'll need to be careful about this, because this book uses the sharp brackets. So when you're working on your homework, don't put the parentheses in, or else it's going to count things wrong. Okay? But there's another reason why this is written kind of like a point, right? This should remind you, it's reminiscent of a point, right? And that's because a vector in standard position right, which the book often calls a position vector. this is a vector centered on the xy axis at the origin. Right? So if I have a vector here positioned at the origin, right, starting at the origin, every vector, when we look at its delta x and its delta y, that's actually going to correspond with its terminating point. Right? Its terminating point here is going to be the point xy, but that's also going to be our delta x and our delta y in this position, right? In this standard position. So the vector v terminating at the point xy in standard position is represented as v sharp bracket x comma y. Okay, so the reason I'm a stickler about using this different notation is because in this case the vector is the vector xy, right? It travels x in the x direction, y in the y direction. However, with parentheses, that's the point xy. Okay, so it's the difference between the bracket guy is the arrow pointing to the point, while the guy here in red is just the point. That may seem kind of abstract, but it can be tough to tell which one we're talking about in context if you use parentheses. And I know some books do it. I actually prefer to use the brackets in at this level of mathematics, just to make sure when you see that sharp bracket, you know we are talking about a vector. When you see the parentheses, you know we are talking about a point. And that is going to be a huge deal later on when we get to the very end, when we start talking about multiple independent and dependent variables. All right, so this is how we sort of define a vector or talk about it in a mathematical sense. This kind of gives us the direction, right? We're talking about the direction because it gives us a delta x and a delta y, how much it changes in the x direction, how much it changes in the y direction. What about magnitude? Well, since we've made a triangle with all of these, right, each vector we looked at, we made a triangle, and therefore, and specifically it's a right triangle, so we can actually use the Pythagorean theorem to find the magnitude. All right, and that's actually not too bad. If we have a vector that goes x and y, we just use the Pythagorean theorem, which tells us, let me call this L for the length, okay, that L squared is equal to x squared plus y squared. And therefore that tells us L is plus or minus the square root of x squared plus y squared, and we are going to only use the plus one here because we're talking about a length, and the magnitude is always positive. Okay, so the magnitude is just the square root of x squared plus y squared. All right, so we denote it this way, that the magnitude of the vector xy is, we use absolute value bars, so you can almost think of the absolute value, but the magnitude of v is the square root of x squared plus y squared. Some books will use double bars, which that's fine, but we go ahead and use just the single bars. And you might get a little confused from absolute value, but the thing is, absolute value, one of its definitions in the 1D case, okay, is actually the square root of x squared. Right? Because if you think about it, if you put a 5 in, well, you'll take the square root of 5 squared, so that would be the square root of 25, which is 5. And if you take this absolute value of -5 and put it in this formula, well, you'll take the square root of -5 squared. Well, squaring a negative makes it positive, so That would be the square root of 25, which is 5. So it turns out that the magnitude is really just a generalization of the absolute value in one dimension, right? And if you think about 1D as just the number line, let's say this line here is the number line I just drew, x is technically a one-dimensional vector that just points from the origin to x. Okay, so it turns out that vectors are really a two-dimensional generalization of just numbers, because you can think of just whole numbers as a one-dimensional vector on the number line. Now, you know, that's super abstract. We're not going to really, you know, get deep into the weeds into that. However, there's a reason why this notation is the same. It's because it's literally just the formula expanded to 2 dimensions, and we'll see something very similar for 3 dimensions. All right, one last thing I want to talk about before we start moving from this, just the definition, equality, that kind of thing, and start talking about operations, is I want to talk about a different way to define vectors. So here we talked about it in terms of its distance left and right versus up and down, right? That's very natural, but suppose you don't have that. Suppose direction is given to you in terms of an angle, and you're given the magnitude. Okay, so if you are given an angle and the magnitude, you can still get your vector v into standard form using trig, using what we know about right triangles. Okay, so if instead we're given the magnitude of a vector and say the angle it makes with the positive x-axis, that's theta here, we can use trig to get it into standard form, because if we think about this, and let's say I look at sine theta, right? Sine theta is opposite over hypotenuse, so that's going to be y over L, which L was our magnitude. So if I move that over, y is going to be equal to the magnitude of v, which is just our L here, times sine theta. Right, so that's our y component. And we can do the same thing with x, just with cosine. So we end up getting the vector v is, bracket, will be the magnitude of v cosine theta, comma, magnitude of v sine theta. All right, this right here is extremely important. We will see this guy a lot. Okay, so get used to that. Basically, length cosine theta, length sine theta. That is, again, I can't even stress that enough, how often we'll be seeing that. Okay, but if you get it down now, you'll get it. You'll have it already for when we use it again. Okay, so this is what you do if you don't know how the vector is traveling left to right, up and down, but you know what angle it makes and you know its magnitude. Okay, that's the formula you will crank through. All right, so the next big question whenever we come up with a new mathematical object that we're studying after equality is other operations like addition, subtraction, multiplication, division. So are these things defined for vectors? And the answer is with addition and subtraction, the answer is yes. With a multiplication, the answer is sort of. Okay, so, and I'll explain what I mean by that as we go forward. But the one I want to start with is what we call scalar multiplication. Okay, so what is scalar multiplication? So I guess we need to talk about what a scalar is. So a scalar is just a number. Okay, and what I mean by that is it's things like 5, -1, 2, versus a vector, which would be something like 2, 1, 7, 3, -5, pi. Okay, these are vectors. They make the arrows, right? 2, 1 would look something like this. Right, 7, 3 would look something like this. -5 pi, probably something like this. Okay, well, these are just numbers. So what scalar multiplication does, it's actually in the name. Remember when I said that when you double the length of a vector, you're doubling the force? Okay, so if our vector v equals let's just say x, y here. 2v, okay, would be 2 times the vector xy, and you really just multiply both components by 2. Okay, so you double both components. So that's scalar multiplication. Scalar multiplication is done component-wise. So this is when you multiply a vector by a scalar. Okay, and it's called a scalar because it scales the vector. Right? So in this case, 2v scales the vector by a factor of 2. And in other words, it doubles v. It doubles the magnitude. Right? And we can actually test that. If I calculate the magnitude of 2x, 2y, well, that's going to be the square root of the x component squared, which would be 4x squared, plus the next component squared, so that would be 4y squared. And here we can actually factor out that 4. And the square root of 4 is, of course, 2. So this comes out to be 2 times the square root of x squared plus y squared. And there we have it, 2 times the magnitude of v. So the magnitude of 2v is double the magnitude of v. So when you multiply a vector by 2, you're doubling the force, but it turns out you're not actually changing the direction. Let me show you with an example. All right, so let's consider the vector 3, 1. Okay, if I multiply 3, 1 by 2, I'm going to get the vector 6, 2. All right, so I have a piece of software that helps me graph these in much nicer ways than I can by hand, so let's jump over. All right, so as you can see, here's the vector 3, 1. We go out 3 and up 1. Okay, so now I'm going to graph the vector 6, 2. All right, so now here's the vector 6, 2 here in the purple, and you can see that it is actually double the vector we started with, right? It has twice the length, because you can see that the original vector takes up this little 3 square rectangle. This one takes up this one and this one. It's double the length, same exact direction. Okay, so scalar multiplication scales the vector. What about multiplying by fraction? Or you could think of it as dividing by 2, right? If I have v over 2, that's going to scale the vector down by a half. Okay, so let's take a look at that on the graph. Okay, so here's our original vector v, and then here is half of v, right? So as you can see, once again, it scales it by half, but doesn't actually change the direction. Hence, scalar multiplication. All right, and finally, if I want to multiply by a negative number like -3 here, we, of course, when you do it component-wise, get -9, -3. If we graph that, well, you could probably tell just by what we already know about vectors is that this is going to be going left instead of right and down instead of up. Okay, so let's take a look at the graph. Okay, so as you can see here, our original vector, and when I graph -9, 3, it goes right off the graph because we don't have it all the way out to 9, but here we go. If I move over, and you can see it is parallel to original vector, but in the opposite direction. So negative numbers flip it around into the opposite direction, but are still parallel to that original vector. So all they're doing is scaling. Okay, so that's scalar multiplication. What about vector addition? Well, we do have vector addition, and it works exactly how you would think. If you have a vector v, which is, let's say it's v1 comma v2, and you have a vector w, which is w1 plus w2, when you add them, you basically just add them component-wise. You take component 1 of v, add it to component 1 of w, put it in the first component, and then you take v2, second component of v, and add it to the second component of w, which is w2. Okay? It's, you know, fairly straightforward. It's how we would expect it to work. The question is, what is it? Why do we talk about it? Because right, scalar multiplication is completely determined, or it comes straight from the fact of what vectors are supposed to be. The fact that if you double a vector, you're doubling the magnitude, right? You're doubling the amount of force. It makes sense that if you multiply a vector by 2, that it doubles the magnitude but not the direction. So the question is, what is this addition do for us? In other words, what does vector addition mean? Why would we want to even talk about it? So let's look at an example. Let's say we have the same v that we did before, which was, say, 3, 1. And then I'll pick a w, which will be, let's say it's, let's do 2, -4. Okay? Throw a negative there. So v plus w, right, that will be the vector 3, 1 plus the vector 2, -4, right, which we just do it component-wise. It'll be 3 plus 2, and then 1 minus 4. Now, just for the record, I won't be doing it as explicitly this way every time, but just for early days here, I think it can be helpful. So we'll get the vector 5, -3. Okay, so let's look at a graph and see what's happening here. Okay, so here are vectors. Here's the vector v, right? Here's the vector w. And when we add them, we get this vector. Now, what this vector is giving us, this is actually what we call the resultant force. It's the combination of these two forces acting together. So imagine if we had a rock here at the origin, and then say I'm here pulling in this direction, and someone else is pulling in this direction with this magnitude, right? So here's my force, and I'm weaker than my friend here who's pulling at this force. If we are pulling on this rock, me in this direction, someone else in this direction, this is the direction the rock will actually move in, and the force at which it will be moving in, right? So the combined force of our two, the two of us pulling, okay? So this is called the resultant force. All right, so V plus W gives the resultant or combined force of V and W acting on the same point or object. Okay, so it gives the new direction that, say, the rock would be moving in, and the total combined force that it will be pulled with. Okay, another thing to look at. All right, so another way to think about this addition of vectors is actually geometric. So if I take the vector V, right, and the vector W and create a parallelogram out of them, like so. See, all I've done is taken a copy of V and moved it down here to make a parallel, and then taken a copy of W and moved it over here, made it parallel. We'll see that the resultant vector, the addition, is actually the diagonal of the parallelogram made from vector V and W. All right, so V plus W forms the diagonal in the parallelogram formed from V and W. So, but notice there's two diagonals. So it's always going to be the vector that points or starts in between V and W, right? It won't be this one that starts at one of them and ends at the other one, but we do have a vector that gives us that. Okay, so let's take a look at subtraction and see what we get there. All right, so V minus W is actually, there's not much to say. It's really just V plus negative W. So negative W is just W flipped around. So, you know, it'll be the vector V1 minus W1, V2 minus W2. So it really, you just take your W, flip it around, and then do the normal resultant. So it's just, instead of W acting on the object, it's going to be the W in the opposite direction acting on the object. Okay, so in the example we looked at before, V minus W, which was our 3, 1, right? And it'll be minus 2, negative 4. I had to look that up, actually. Couldn't remember what the second one was. So it'll be 3 minus 2 in the first component, and then 1 minus a negative 4. So that's the only thing to really be careful about here is how the signs play with this. Okay, so we'll have the vector 1, and then this will be 1 plus 4, so we'll have the vector 1, 5. So let's look at some of this stuff on the graph. Okay, so on the graph here, here's our V, and then here's our W, and then our negative W is right here, right? It's just going in the opposite direction. And then that subtraction that we just calculated is here, and as we can see, it does form a diagonal of these two vectors. It's the resultant of these two vectors, right? So all the subtraction is, it's just a form of addition where you're just negating one of your vectors. However, if I were to take this vector and move it here, right, we'll see that it makes the other diagonal of the parallelogram. Okay, which is what I've done right here. I've taken this vector and moved it here, and we see that the subtraction makes the other diagonal that goes from the tip of the subtracting one and moves to the tip of the first one. So the tip of W to the tip of V. And I know this can maybe seem a little funky because we're not used to just being able to move things around and have it be the same object, but just think about how things work in, objects work in 3 dimensions. If you think of a vector as maybe your pen, it's the same pen if you move it from your table to your floor, right? The direction might change, so that would make it a different vector, right? But if you keep the direction exactly the same, it's going to be the same pin pointing in the exact same direction. All right, so once again, v minus w forms the other diagonal of the parallelogram. Okay, to end up this particular video, let's take a look at an example. All right, let's say we have a boat. It's traveling along a river, and let's say it's doing so, it's going due east, okay, at, let's say, 50 miles an hour. That might be kind of fast for a boat, but whatever, it's just going 50 miles an hour. But while it's traveling, right, so it's traveling along a river. So if they are actually pointing the boat due east, all right, that doesn't actually mean they're going due east. In fact, it turns out that the river has a current. So it's actually pushing the boat back. So it's pushing back against the boat and actually traveling, let's say it's traveling at exactly southwest. Okay, so if it's traveling southwest, and let's say it's not traveling super fast, maybe like, I'm going to say 2√2 miles per hour, and you'll see why I did that in just a second. It's going to make our math a little easier once we get there. Okay, so I want to find, so sorry I didn't write out the words here. I figured a picture would just be easier to deal with, but we want to find the actual direction and velocity the boat it travels in. Right, now we can do this same problem with trains, or maybe not trains because they're stuck on a track, but planes. We can do this with planes. We can, there are so many different ways we can set up a problem like this using vectors. So the actual direction and velocity, well, that's going to be the resultant vector. Right? So based on what we've just talked about, what happens is if the boat is exactly facing due east and traveling, the current of the river is going to push it off course. So usually if a boat wants to travel due east and the current is pushing it to the southwest, it will want to point up to the north a bit to counteract the push of the current. However, this boat's not actually doing that right now. So we just want to see how far, basically how it's pushing it off course. Okay, so really we want to find the resultant vector. Okay, so we need to start by finding the two vectors we already have. Well, hopefully this one isn't too difficult to figure out, because if we put the boat right on the origin, 0, 0, this is going to be a vector that goes from the origin to the point 50, 0. Okay, so this, I'll call it B. The vector B is equal to 50, 0. So this is the speed of the boat. Okay, and then R, okay, R is going to be the vector for the river. Now I don't know what it is in terms of X and Y. All I have is the magnitude and the direction, right? So at exactly southwest, this is going to be like a 45-degree angle to here. So that's going to be a multiple of pi over 4. So that should be 5 pi over 4. Okay, so it'll be the vector composed of the magnitude 2 root 2 times cosine of 5 pi over 4, comma 2 root 2 sine of 5 pi over 4. Now what's nice about this, since this is quadrant 3, we know both of these are negative, and they're both, since it's multiples of pi over 4, they're both going to be square root of 2 over 2, and that's actually why I put the root 2 into here. All right, so this was going to be the vector negative 2 root 2 times root 2 over 2, and then negative 2 root 2 square root of 2 over 2. Okay, so the 2's cancel, and the 2 square root 2's come out to just be 2. So this ends up being the vector negative 2, negative 2. All right, so the resultant vector, which I already used R, so I'll use C for the combined. I already used pink for that, so the combined forces together will be B plus R. Okay, so it'll be the vector 50, comma 0 plus the vector negative 2, comma negative 2. Okay, and then that is going to be 48, comma negative 2, which looks right to me, actually. 48 negative 2. Okay. All right, so the actual velocity the boat is traveling in, we can calculate with the magnitude. So that'll be the square root of 48 squared plus negative 2 squared. Right, and we'll likely need a calculator to crank this out. All right, so this comes out to be about 48.04-ish. All right, so that will be in miles per hour, which kind of makes sense if you think about it, because notice that the current is actually pushing against the boat, right, in the opposite direction that it wants to travel. If, on the other hand, the current was, say, pushing this way, it would actually be speeding up the boat. But here, it's just slowing it down a little bit, and it pushes it off course by a little bit as well. And how we figure that out is with some trig. Okay, so we're going to try and figure out what this angle is. All right, and I think the best way to do it is, since this is not a right triangle that we just made, instead of trying to set up a right triangle, just use, well, I mean, I guess we do have the right triangle now that I said it, because that would be negative 2. What I mean to say is, instead of using the hypotenuse, which is this nasty number, we might as well just use tangent, since we have the x and the y. Right, so tangent theta is sine over cosine, so it's going to be y over x. So in this case, it's going to be the negative 2 over 48, also known as negative 1/24, and then we're just going to take tan inverse of that and see what we get. All right, and provided I did this correctly, I got about negative 2.39 degrees, which makes sense. This, first of all, this is definitely not drawn to scale, okay? And the water's only pushing it off course by just a little bit, right? There's not a huge, it's not going super fast, it's not super violent river. So it only knocks it off course by about 2 degrees in the negative direction. Right? That's what the negative is telling us here. I use degrees here. You could use radians. For physical applications like this, a lot of times the degrees make more sense visually to us. But when we start getting to, if we're talking about time, Right? If our angle is time, then we always need to use radians, because degrees don't really make any sense when we're talking about in time units. Okay, so that's definitely enough for one video. In the next one, which will be part 2 of this vector basics, we're going to look at how this all transfers over to 3 dimensions, and spoiler alert, most of it transfers exactly, right? The only tricky part about it is the visualizations, but the math is pretty much all the same. Okay, so I'll catch you all on the next one. Cheers.